Assalamu alaikum jami'an, good afternoon everyone. Now we're going to start with chapter 5 where we're going to talk about gas liquid separator. And as we mentioned earlier, or as you still remember from the process flow diagram for a natural gas plant, the first unit will be where you're going to separate the gas from the liquid before you go for the dehydration or for the acid gas removal. So the first unit, and we're going to see this on the detailed flow sheet slide that we're gonna present later on. But now in this chapter, which is chapter 5, we're gonna discuss mainly the gas liquid separator or the gas liquid separator design, and we're gonna look at the configuration, vertical, horizontal, different configuration for the gas liquid separator, which is something that's not new to you as well, because you have seen this before in several courses maybe. So we're going to look at how we're going to use these principles that you have learned before in terms of gas liquid separator in order to be used or to design it for natural gas processing. And this is what we're going to be exposed to in chapter 5, mainly the gas liquid separator, which is the first unit or the first processing unit we can think of in the basic natural gas processing flow sheet. In this slide, I'm going to present again the classification of the natural gas compound that we have seen before. And I still remember that we have discussed this slide before that, but I'm giving it to you here as just to refresh your memory about the difference between the LNG, the LPG, the NGL, and what do you mean by, for example, LNG, liquefied natural gas, and NGL, which is natural gas liquids, LPG, which is liquefied petroleum gas, and the definition of most of these compounds as we have seen it before in the introduction of chapter 1. So this is, I'm just giving it to you again to refresh your memory about the things that we're going to discuss again, because this is like terms that we're going to see it more frequent once we go through the course material. So please make sure you still remember these terms. Now we're going to talk about the flow sheet or the process flow sheet for the natural gas processing. And as you still remember, we said that there are two types of flow sheets. We have the detailed one and we have the simple one. And this is one of the detailed flow sheet that we're going to see more frequent in this course. And you have seen it before in chapter 1. This is just to give you an idea about what we are going to talk about in this section. So now we are talking about this unit, which is the first unit, which is, I'm going to call it separation unit in general. Separation unit. Or to be more specific, I'm going to call it gas liquid separation unit. So this is what we're going to discuss now in chapter 5. So where we are here right now is here. So this is chapter 5. And in chapter 5 we're going to talk mainly about what's going on in this unit, or the gas liquid separator unit. We're going to talk about the basic principle of the gas liquid separation, what are the main mechanism for that separation, and then we're going to talk about the design, and then we're going to talk about the configuration of these gas separators. So in chapter 5 we're going to talk all about this region or this area or the first unit, where we're going to split or separate the gas from the liquid stream before we go to further processing units such as the sweetening and the dehydration and the NGL separation, nitrogen separation, helium separation, and liquefaction steps. Now, to understand the basic principle of how the gas liquid separation process took place, let's look at this diagram here that represents a liquid droplet that has a diameter of what we call dp, and you can imagine that this liquid droplet is entrapped in a gas stream. So you have this this liquid droplet. Imagine that it's water, for example, that has a specific diameter. Let's say diameter is approximately dp, and this liquid droplet is entrapped in in a gaseous phase. So now if we want to look at the force balance of on this liquid droplet, we have mainly two force balance on this droplet. So the first, and you have to imagine that the gas flow or the gas velocity is going upward in this direction. So just let me choose different color. So now if you want to imagine, or if you want to establish the force balance around this droplet, so you have basically two types of forces. So you have the first type of forces that drag or that bring the droplet down, which is called the gravitational force of the droplets. So first force is the gravitational force that bring the droplet or push the droplet down. And you have also other type of forces, which is called the drag force, which is the force coming from the flowing of the air that's gonna move the gas droplet upward. So you have two forces. You have drag force up and you have gravitational force down. Now what will happen? The liquid droplet, this liquid droplet will settle down or will precipitate or will settle down in case you have the gravitational forces is much higher than the drag force, or at least it's equal or higher than the drag force. So in order for the liquid droplet to settle from the gas stream or to take it out from the gas stream, the gravitational force, or let me call it gravitational force on the droplet, must be greater than the drag force. So this is like physical explanation, or this is simple physical meaning or mechanism for the separation of liquid from the gas stream. So the first thing you need to understand that you have a balance of forces. You have a force that push the liquid droplet upward, which is the drag force, and you have another force that bring the liquid droplet downward, which is the gravitational force. Once the gravitational force is greater than the drag force, then the droplet will precipitate or will settle out of the gas stream. So now another thing that we need to keep in mind that we can classify the gas liquid separator also based on two categories based on the amount of the gas to liquid ratio that you are dealing with. If you are dealing with high gas to liquid ratio, then this can be considered as what we call the knockout drum or the scrubber. If you are dealing with a scenario where you have low gas to liquid ratio, this means that you are dealing with what we call a flash tank or what we call the oil gas separator in general. Normally you will use not single stage, you will use multi-stage separation unit or gas liquid separation unit, for example. In this scenario, you're going to combine what we call the high pressure separator with what we call the low pressure separator, where at the first stage you take the high pressure separator, will separate part of the gas, and the gas will be taken to gas compressor to be pumped as a natural gas into the pipeline and or for further processing. And then the second stage, where you take the bottom part of the separator or the high pressure separator, you bring it to at what we call the low pressure separator, and the low pressure separator will further separate the gas from the liquid, where the gas also will be taken again to what we call booster compressor, where it's going to compress the gas again and pump it again to the gas compressor for further separation or for pumping in the pipeline as well in some cases. And this is very appropriate scenario, or this is very profitable scenario, because most of the time you will optimize or you will maximize the separation of the gas from the liquids in this scenario. But again, you have to look at the cost of this scenario as well, because normally when you add further separation step or further stages of separation, high combined with low, this means that you're gonna include more of the capital cost and the operating cost as well. But you need to keep in mind that also this will result in more efficient separation. Now we're going to look at basic mathematical formula that describe something called the VT, or something called the critical or terminal gas velocity needed for the particle of dB to be or to drop out or to settle out of the gas stream. And this VT will be a speed or velocity, or what we call a critical or terminal velocity that I need in order for this water droplet of a specific size to be settled out or to be removed from the gas stream. So how can, as we mentioned earlier, that the liquid droplet will be removed from the gas stream if the gravitational forces acting on that droplet is greater than the drag force. Therefore, I can simply find the VT, or the terminal velocity, or the critical velocity, as per this mathematical formula, where dB stands for let me just use different color, okay, where dB stands for the particle size of the liquid material or liquid droplet. Rho g is the density of the gas. Rho L is the density of the liquid, and g is the acceleration of gravity, which is a constant or fixed number. And in this formula you can use also AP, which is the surface area of the, or the particle or surface area or cross-section area of the droplet. of the liquid droplet. And MP also referred to what we call the mass of the droplet, of the liquid, I mean, mass of the droplet, which is the liquid in fact. So one thing we need to keep in mind is the CD, which is the drag coefficient of the particle, which is a dimensionless number, CD, where CD is in fact the drag coefficient of the particle, which is a dimensionless value or a dimensionless number that you can or you need to calculate based on graphical calculation or based on trial and error sometimes, and we're going to see how we're going to do it later on. So this is the basic formula to calculate Vt, which is the minimum velocity or the critical or the terminal velocity required for me to remove, or for any system to remove, a particle of liquid or droplet of liquid from a gas stream. But this droplet has a specific mass, has a specific dimension, has a specific size as well. So now how can we find the drag coefficient? We need to find what is the drag coefficient, or CD. How can we find the drag coefficient? We can find the drag coefficient based on this formula, which is CD multiplied by Reynolds number square equal to this formula. But again, you have to keep in mind that this CD or the drag coefficient is a function of dB again, and it also function or depends mainly on Reynolds number. And as per definition, Reynolds number is also function of two things, of dB and Vt. And we know from the previous slide that Vt is also a function of dP. So this means that in order to find the drag coefficient, I need to find Reynolds number and dP. And in order to find Reynolds number, I need to find how much is the particle size and how much is the Vt. And Vt is in fact function of dB. Therefore, I need to apply what we call a trial and error approach in order to get a rough estimate or a good estimate for the drag coefficient. So how do we do the coefficient? There are three cases or two cases that we're going to be exposed to when we around, or to find how can we find the Vt, for example. The first case where you have very low Reynolds number, less than 2, you can assume that this is like a stock law, and you can assume that there is a linear relationship between the drag coefficient and Reynolds number, and as a result I can simply find Vt based on this formula, okay, where dB also, or the particle diameter or the droplet diameter, can be also found using this formula straightforward. If I know the mu, which is the viscosity of the continuous phase, which is in fact the gas in this case, rho g is the rho of the gas, rho L is the density, and there is something called KCR, which is a constant, or what we call the proportionality constant. And the proportionality constant can be assumed to be approximately 0.033 if the Reynolds number is less than 2, which means that I'm applying Stokes law. So this is a way how to find an estimate for Vt. And how we do that? First, we estimate how much is dB. If you have a very low Reynolds number, if I assume that you have low Reynolds number, this means that you are applying Stokes law, where you can assume that there is a linear relationship between Reynolds number and drag coefficient. Therefore, I can find Vt if I know how much is dB. And dB, I can find it simply if I know the physical property of the system, if I know the viscosity and the density of the gas and the liquid. And I know something called KCR, which is a constant, or this is what we call proportionality constant, which can be estimated to be 0.033 for Reynolds number less than 2. So this means that I can find dB, and if I find dB, I can find how much is Vt. If I find Vt, then I can find how much is the Reynolds number and assure that Reynolds number is less than 2. And then I can bring all these values into this equation that I'm gonna put it now in green to find how much is the drag coefficient. So this is the first case, or this is the first scenario, or the simplest scenario, how to calculate the drag coefficient for Stokes law region where Reynolds number is less than 2. Now the second case, if you have an intermediate law, which means that Reynolds number is between 2 and 500, and therefore you need to apply what we call the intermediate law, where the terminal velocity also can be found using this formula, which is again a function of the physical properties of the system, rho of the gas, rho of the liquid, viscosity of the gas, and the diameter of the particle. But in this case, you have to keep in mind that you cannot use the formula that you applied before to find how much is dB. No, you need to apply a new formula for dB, and you can find how much is the diameter of the droplet using, again, based on the physical properties of the system, viscosity and density, and based on the proportionality constant, which is KCR. But in this case, the KCR for this Reynolds number value has to be approximately 0.435. And the last one, which is the Newton's law. Newton's law, when you have, for example, Reynolds number greater than 500 up to 200,000. This means that you can simply find the VT based on this formula. Okay. And normally this formula will be applied in case you have large droplet or large dB, and normally you will get drag coefficient of approximately 0.44 if you have a Reynolds number greater than 500. This means that if I find how much is VT, or the critical velocity, I can simply find how much is the cross-sectional area of the separator that I'm looking for, where cross-sectional area will be QA, which is the flow rate of the gas, for example, divided by the critical velocity. If you have, for example, vertical separator, if you have horizontal separator, then you can use this formula, where L in foot, QA in foot cube per second, VT in foot per second, which is the terminal velocity, dV in foot, which is the diameter of the vessel, dB is the diameter of the particle. So this is the difference between dB and dV. dV is the vessel diameter, and dB is the particle diameter, and rho is the density, and mu is the viscosity. So you can calculate if you have, for example, horizontal using this formula, and if you have a classical, or you can say it's for any vertical separator, you can use this formula in general. But here you have to keep in mind that this formula is applicable if you have the separator with no mist, doesn't have the mist eliminator that we're going to be exposed to later on, and we're going to see what do you mean by mist eliminator later on. Now you can also use the chart to find how much is the CD, or the drag coefficient. If you know the value of CD Reynolds number for certain range for specifically spherical material or spherical droplet, you can simply find how much, for example, will be the CD for a specific value of CD multiplied by Reynolds number to the power 2.